Now we generalize the calculation of the moment of inertia based on the approximation of rigid bodies with rigid systems of point masses. As already seen, the moment of inertia I of a rigid body with respect to the z-axis in the approximation using a system of n point masses is given by the sum of the mass mi of the point mass mi times the square of the distance di of the point mass from the z-axis. Here the square of the distance di is equal to the square of the x-coordinate of the position vector ri of the point mass, plus the square of the y-coordinate of the position vector. We also saw that the moment of inertia has the same role in the case of rotations about an axis as the mass for point-like bodies performing translational motion. Furthermore, this quantity depends on the distribution of the mass of a body with respect to the axis of rotation, as the formula shows. In the approximation using a rigid system of point masses we can follow the same procedure as in the case of the calculation of the center of point mass of rigid bodies, where we consider the point masses as the mass elements delta mi, given by the average density ρ I of the mass element times the volume delta Vi of the mass element. In the limiting case the number n of the mass elements tends to infinity while their volume delta Vi becomes the infinitesimal volume element dV shrinking to 0. For a realistic mass distribution represented by the density ρ of the body, the infinite sum converges and its limit will be a volume integral. Then the moment of inertia I of a rigid body of volume calligraphic V with respect to the z-axis can be written as the integral of the density ρ of the body, times the square of the distance d of the volume element in the integral from the axis of rotation, over the volume calligraphic V of the body. The square of the distance d in the integrand can be replaced by the sum of the square of the x-coordinate and the square of the y-coordinate, where the volume element is the function these Cartesian coordinates. As an example, we determine the moment of inertia of a homogeneous rod of length L and cross-sectional area Q with the uniform density ρ with respect to the z-axis perpendicular to the rod. In the first case the axis passes through the center of mass C of the rod, and it passes through one of its ends in the second case. Here the center of mass C is at the middle of the homogeneous rod of constant density. Because the volume element dV of the rod can be written as the product of the cross-sectional area Q of the rod and the infinitesimal length dx measured along the rod, the moment of inertia I of the rod with respect to the axis passing through its center of mass is given by the integral of the density ρ of the rod, times the square of the distance x from the center of mass C, times the cross-sectional area Q with respect to the distance x from minus the length L over 2 to plus the length L over 2. Here ρ and Q are constants and the integral of x squared gives x cubed over 3 evaluated at the limits of the integral. As a result, we obtain ρ times Q, times the cube of L over 12, where we can use the relation for the density ρ of the rod expressed as the mass m of the rod over the cross-sectional area Q times the length L, and state that the moment of inertia of the rod with uniform density with respect to a perpendicular axis passing through its center of mass is equal to 1 over 12 times the mass m of the rod, times the square of its length L. If the axis of rotation passes through its one of its end, then its moment of inertia I is given by the density ρ times the cross-sectional area Q, times the integral of the square of the distance x from the end which the axis passes through with respect to this distance from 0 to the length L. Here the integration gives L cubed over 3, and the moment of inertia I of the rod with respect to a perpendicular axis passing through one of its end is equal to 1 over 3 times its mass m times the square of its length L. In many cases, the moment of inertia I of a rigid body of mass m can be written as the mass m times the square of the radius of gyration k, where the body is replaced by the point mass m at the distance of the radius of gyration k from the axis of rotation. The results obtained for the homogeneous rod can be seen in the first line of this table showing the moment of inertia I of solids of uniform distribution of mass, that is of constant density with respect to different central axes. The third and fourth lines contains the moment of inertia of a cylinder of radius r and height h with respect to its axis of symmetry, which is equal to 1 over 2 times the mass m of the cylinder, times the square of the radius r, and with respect to a central axis perpendicular to the symmetry axis, which is equal to 1 over 4 times m times r squared, plus 1 over 12 times m times the square of the height h. In the first line of the second table we can see the moment of inertia I of an empty cylindrical shell of an arbitrary height with respect to its symmetry axis, where r1 and r2 are the exterior and interior radii of the shell. Here the moment of inertia is given by 1 over 12 times the mass m of the shell, times the sum of r1 squared and r2 squared. The second line shows the moment of inertia of a rectangular cuboid of length a, width b and height c with respect to the vertical central axis, which is equal to 1 over 12 times the mass m of the cuboid, times the sum of the square of its length a and the square of its width b. In the third line we can see the moment of inertia of a cube of side a with respect to any of its central axis parallel with its edges, which is given by 1 over 6 times the mass m of the cube times a squared. The first line in the last table shows the moments of inertia I of a sphere of radius r and a thin spherical shell of the same radius with respect to any of their central axes. The moment of inertia for the sphere is given by 2 over 5 times the mass m of the sphere times r squared, whereas I is equal to 2 over 3 times the mass m of the shell times r squared for thin spherical shell. In the second line we can see the moment of inertia of an ellipsoid with semi-axes A, B and C with respect to the central axis in the direction of the semi-axis C, which is given by 1 over 5 times the mass m of the ellipsoid, times the sum of A squared and B squared. The last example is the moment of inertia of a circular cone of radius r and arbitrary height with respect to its symmetry axis, which is equal to 3 over 10 times the mass m of the cone times r squared. Now we prove the Huygens-Steiner theorem on the rotation of rigid bodies about parallel axes, attributed to the polymath Christian Huygens, who also introduced the concept of moment of inertia, and later generalized by the Swiss mathematician Huygens-Steiner. Let us consider two parallel axes passing through the points A and C of a rigid body where C is the center of mass of the body. Here the figure shows the cross-section of the body in a plane intersecting both the points A and C. The axes passing through the points A and C are perpendicular to this plane. The axis passing through the center of mass C of a rigid body is also called the central axis of the body. Obviously, the central axis of a rigid body is not unique since its direction is arbitrary. Now the direction of the central axis has the same direction as the axis passing through the point A. We attach a Cartesian coordinate system to the point C such that its z-axis is the central axis of the body and the straight line connecting the points A and C is the x-axis. The distance between the two parallel axes is given by d, as seen in the figure. Let IA denote the moment of inertia of the rigid body with respect to the axis passing through the point A. Similarly, IC will denote the moment of inertia of the body with respect to its central axis, that is the axis passing through its center of mass C. We apply the approximation with a rigid system of point masses mi, where any point mass mi at the point P of the body has the coordinates xi and yi in the coordinate system attached to the central axis of the body. Here di denotes the distance between the point P and the central axis, and the distance between the point P and the axis passing through the point A is denoted by d bar I. Because the position of the point P is arbitrary within the body, these distances are always measured in the plane perpendicular to the parallel axes that intersects the point P. Then we can write the moment of inertia IC of the body with respect to its central axis as the sum of the mass mi times the square of the distance di of the point mass from the central axis, from I equals 1 to the number of point masses n. This is equal to the sum of the mass mi times the sum of the square of the x-coordinate of the position of the point mass mi and the square of the y-coordinate of its position, from I equals 1 to n. Similarly, the moment of inertia IA of the body with respect to the axis passing though the point A is given by the sum of the mass mi times the square of the distance d bar I of the point mass from the axis, from I equals 1 to n. Here the square of the distance d bar I can be expressed as the square of the difference between the xi coordinate and the distance d, plus the square of the yi coordinate. By removing the bracket we obtain the sum of mi times the sum of xi squared and yi squared from I equals 1 to n, plus d squared times the sum of mi from I equals 1 to n, minus 2 times d times the sum of mi times xi squared from I equals 1 to n. We can recognize the moment of inertia IC in the first term in the right-hand side, whereas the sum in the second term gives the total mass of the system of point masses approximating the rigid body, that is the mass m of the body itself. Because the x-coordinate of the center of mass C of the body is given by 1 over the mass m times the sum of the mass mi times xi from I equals 1 to n, which vanishes in the coordinate system with the origin at the point C, the last term in the right-hand side also vanishes. This result can be summarized in the Huygens-Steiner theorem as follows: if IC is the moment of inertia of a rigid body of mass m with respect to its central axis, that is an axis passing through the center of mass of the body, then the moment of inertia I of the body with respect to a parallel axis at the distance d from the central axis is given by the sum of the moment of inertia IC and the product of the mass m and the square of the distance d. As an application of the theorem, let us calculate the moment of inertia of a rod of length L and mass m with a uniform density with respect to the axis passing through one of its end that is perpendicular to the rod. We saw that the moment of inertia IC of the rod with respect to a perpendicular axis passing through its center of mass C is equal to 1 over 12 times the mass m of the rod times the square of its length L. Since the distance between the center of mass C of the rod and any of its end is the half of its length, the theorem states that the moment of inertia I is equal to 1 over m times L squared, plus m times the square of L over 2. Because the second term in the right-hand side of the equation can be written as 3 over 12 times m times L squared, the moment of inertia I of the rod can be written as 1 over 3 times the mass m times the square of the length L, as we expected. We consider a more general situation where the origin O of the Cartesian coordinate system used to describe the motion of the rotating rigid body is still located on the axis of rotation, but the later forms the angles alpha, beta, and gamma with the coordinate axes x, y, and z, respectively. Then the components of the unit vector E in the direction of axis of rotation are the cosines of the angles alpha, beta, and gamma that the vector makes with the coordinate axes, called direction cosines. We will determine the moment of inertia denoted by I sub alpha beta gamma of the rigid body with respect to the axis with the direction described by the angles alpha, beta, and gamma with respect to the coordinate axes. In the approximation applying a rigid system of n-point masses, any mass element of the body is represented by a point mass mi, which has the position vector ri with respect to the origin O, where the components xi, yi and zi of the position vector describe the position of the point mass in space. Then the moment of inertia I sub alpha beta gamma is equal to the sum of the mass mi of the point mass mi times the square of the distance di of the point mass from the axis of rotation, from I equals 1 to n. If the point A denotes the projection of the position of the point mass mi onto the axis of rotation, the square of the distance di can be written as the square of the length of the position vector ri minus the square of the distance between the origin O and the point A. Because the distance between the points A and O is given by the scalar product of the position vector Ri and the unit vector E, the square of the distance di between the point mass mi and the axis of rotation can be written as the sum of the squares of the components of the position vector, that is xi squared plus yi squared plus zi squared, minus the square of the scalar product of the two vectors written in terms of the coordinates of the vectors, that is the square of the quantity of xi times cosine alpha plus yi times cosine beta plus zi times cosine gamma. In the right-hand side of this equation we can separate the terms containing the square of the Cartesian coordinates from the terms containing the products of these coordinates. Then the first group of the terms is given by 1 minus the square of cosine alpha times xi squared, plus 1 minus the square of cosine beta times yi squared, plus 1 minus the square of cosine gamma times zi squared. Whereas the second group is given by minus 2 times xi times yi times cosine alpha times cosine beta, minus 2 times yi times zi times cosine beta times cosine gamma, minus 2 times zi times xi times cosine gamma times cosine alpha. Since the sum of the squares of the direction cosines is equal to 1, the first three terms forming the first group can be written as the sum of the square of cosine beta and the square of cosine gamma, times xi squared, plus the sum of the square of cosine alpha and the square of cosine gamma, times yi squared, plus the sum of the square of cosine alpha and the square of cosine beta, times zi squared. By removing the parentheses, regrouping the terms, and factoring out the squares of the direction cosines in the right-hand side, we obtain three terms, the sum of yi squared and zi squared, times the square of cosine alpha, plus the sum of zi squared and xi squared, times the square of cosine beta, plus the sum of xi squared and yi squared, times the square of cosine gamma. If we substitute this result into the original equation, then we can write the square of distance di of the point mass mi from the axis of rotation as 6 terms grouped with respect to the squares of the direction cosines and their mixed products. Now we insert this expression into the equation of the moment of inertia of the body with respect to the axis of rotation described by the angles alpha, beta, and gamma, and we write I sub alpha beta gamma as the following: the sum of mi times the sum of yi squared and zi squared, times the square of cosine alpha from I equals 1 to n, plus the sum of mi times the sum of zi squared and xi squared, times the square of cosine beta from I equals 1 to n, plus the sum of mi times the sum of xi squared and yi squared, times the square of cosine gamma from I equals 1 to n, minus 2 times the sum of mi times xi times yi times cosine alpha times cosine beta from I equals 1 to n, minus 2 times the sum of mi times yi times zi times cosine beta times cosine gamma from I equals 1 to n, minus 2 times the sum of mi times zi times xi times cosine gamma times cosine alpha from I equals 1 to n. It is a lengthy expression, but we introduce a set of notations for the multiplication factors containing the Cartesian coordinates to simplify the result. Then we conclude the following. The moment of the inertia I sub alpha beta gamma of a rigid body with respect to an axis passing through the point O in the direction determined by the angles alpha, beta, and gamma with respect to the axes of the coordinate system with the origin at the point O is given by I sub xx times the square of cosine alpha, plus I sub yy times the square of cosine beta, plus I sub zz times the square of cosine gamma, plus 2 times I sub xy times cosine alpha times cosine beta, plus 2 times I sub yz times cosine beta times cosine gamma, plus 2 times I sub zx times cosine gamma times cosine alpha. Here the quantity I sub xx given by the sum of mi times the sum of yi squared and zi squared from I equals 1 to n, is the moment of inertia of the body with respect to the x-axis of the coordinate system. The quantity I sub yy given by the sum of mi times the sum of zi squared and xi squared from I equals 1 to n, is the moment of inertia of the body with respect to the y-axis of the coordinate system. The quantity I sub zz given by the sum of mi times the sum of xi squared and yi squared from I equals 1 to n, is the moment of inertia of the body with respect to the z-axis of the coordinate system. The quantities I sub xy denoting minus the sum of mi times xi times yi from I equals 1 to n, I sub yz denoting minus the sum of mi times yi times zi from I equals 1 to n, and I sub zx denoting minus the sum of mi times zi times xi from I equals 1 to n are called products of inertia of the body with respect to the coordinate axes. Unlike the moments of inertia which are always positive, the products of inertia can be positive, negative or zero depending on the shape and orientation of the rigid body. They describe how the rotation of a body about one coordinate axis is affected by its shape and mass distribution with respect to another coordinate axis. If the distribution of mass is symmetric about a plane, then the product of inertia vanishes with respect to that plane. For example, I sub xy is equal to 0 if the mass distribution of the body is symmetric about either the xz plane or the yz plane. We note that another convention is also used for the definition of the products of inertia where the minus sign is not included in the definition, reversing the signs of the last three terms in the expression obtained for the moment of inertia I sub alpha beta gamma. In the general case, we define the moment of inertia of a rigid body by a volume integral which also holds for the moments of inertia with respect to the coordinate axes. By assuming that the rigid body has a continuous distribution of mass, the moments of inertia of the body with respect to the coordinate axes attached to the point O becomes volume integrals. For example, the moment of inertia I sub xx of the body with respect to the x-axis is given by the volume integral of the density ρ of the body times the sum of the square of the x-coordinate and the square of the y-coordinate with respect to the volume v over the volume calligraphic v of the body. Here the volume element dv in the integral can be expressed in terms of the Cartesian coordinates x, y and z. Similarly, the products of inertia become volume integrals as well. For example, I sub xy is given by minus the volume integral of the density ρ times the coordinate x times the coordinate y with respect to the volume v over the volume calligraphic v of the body. In order to illustrate the geometric interpretation of the expression obtained for the moment of inertia of a body with respect to an arbitrary axis, let us choose the location of the point P on the axis of rotation that passes through the point O in any direction described by the angles alpha, beta, and gamma with respect to the coordinate axes such that the distance between the points is equal to 1 over the square root of the moment of inertia I sub alpha beta gamma with respect to the axis of rotation. Here the moment of inertia is determined by the geometry and the distribution of mass of the body. If we project the point P onto the coordinate axes, then we obtain the triple key, eta, and theta, which can be used to describe the position of the point instead of its Cartesian coordinates. As the figure shows, the coordinate key can be written as the distance between the points O and P times cosine alpha, that is cosine alpha divided by the square root of I sub alpha beta gamma. Then cosine alpha is equal to key times the square root of I sub alpha beta gamma. Similarly, cosine beta can be expressed by eta times the square root of I sub alpha beta gamma, and cosine gamma by zeta times the square root of I sub alpha beta gamma. After having expressed the direction cosines in terms of the triplet, we can substitute them into the equation obtained for the moment of inertia I sub alpha beta gamma. This gives I sub xx times key squared times I sub alpha beta gamma, plus I sub yy times eta squared times I sub alpha beta gamma, plus I sub zz times zeta squared times I sub alpha beta gamma, plus 2 times I sub xy times key times eta times I sub alpha beta gamma, plus 2 times I sub yz times eta times zeta times I sub alpha beta gamma, plus 2 times I sub zx times zeta times key times I sub alpha beta gamma. Because each term in both the sides of the equation contains the quantity I sub alpha beta gamma, we can divide the equation by this quantity assuming that it is not zero. Then we obtain the equation stating that 1 is equal to I sub xx times key squared, plus I sub yy times zeta squared, plus I sub zz times zeta squared, plus 2 times I sub xy times key times eta, plus 2 times I sub yz times eta times zeta, plus 2 times I sub zx times zeta times key. This expression is the equation of a quadratic surface in terms of the coordinates key, eta, and zeta, where the surface is an ellipsoid. Indeed, the moment of inertia I sub alpha beta gamma defined by the sum of the point masses approximating the body times the square of their distances from the axis of rotation cannot be zero, apart from the cases of a single point mass or a dumbbell model of uniform distribution of mass if the axis of rotation is its symmetry axis. As a consequence of the non-vanishing expression of I sub alpha beta gamma, the quadratic surface cannot be hyperboloid or paraboloid, and we conclude that the equation obtained for I sub alpha beta gamma corresponds to the ellipsoid of inertia related to the point O. Let us consider the axis passing through the point O in the direction given by the angles alpha, beta and gamma with respect to the coordinate axes with the origin O. If the point P is the point of intersection of this axis and the ellipsoid, then the moment of inertia of the body with respect to the axis is given by 1 over the square of the distance between the points O and P. The three mutually perpendicular axes of symmetry of the ellipsoid of inertia that intersect at its center are called the principal axes of inertia. The moments of inertia of the body with respect to the principal axes are the principal moments of inertia of the body, and they are given as follows. The first principal moment of inertia denoted by I1 is equal to 1 over the square of the distance between the points O and capital A, where this distance is denoted by A as seen in the figure. Similarly, the second principal moment of inertia denoted by I2 is equal to 1 over the square of the distance between the points O and capital B, or 1 over the square of the distance B, and the third principal moment of inertia denoted by I3 is equal to 1 over the square of the distance between the points O and capital C, or 1 over the square of the distance C. If we consider the general case, these principal moments of inertia are not equal to each other. In fact, the minimum value of these principal moments is equal to the minimum value of the moment of inertia with respect to any axis passing through the point O. Similarly, the maximum value of these principal moments gives the maximum value of the moment of inertia with respect to any axis passing through the point O. In a special case where all the three principal moments of inertia are equal to each other, the ellipsoid of inertia becomes a sphere, that is, the moment of inertia of the body is the same with respect to any axis passing through the point O. If choose the principal axes of the ellipsoid of inertia as the coordinate axes passing through the point O, then this choice represents a coordinate transformation from the Cartesian coordinates x, y and z to the coordinate x bar, y bar and z bar. This means that we also transform the triplet key, eta and zeta to a new triplet key bar, eta bar and zeta bar. By applying this transformation, we can write the equation of ellipsoid of inertia in canonical form stating that the principal moment of inertia I1 times key bar squared, plus the principal moment of inertia I2 times zeta bar squared, plus the principal moment of inertia I3 times zeta bar squared is equal to 1. Or equivalently, key bar squared over the square of the distance A, plus eta bar squared over the square of the distance B, plus zeta bar squared over the square of the distance C is equal to 1. The products of inertia of a rigid body therefore vanish in the principal axis system of the ellipsoid of inertia associated with a rigid body with respect to a given point O. As a result, the moment of inertia I sub alpha beta gamma of a rigid body with respect to an axis passing through the point O in the direction described by the angles alpha, beta and gamma in the principal axis system is equal to the principal moment of inertia I1 times the square of cosine alpha, plus the principal moment of inertia I2 times the square of cosine beta, plus the principal moment of inertia I3 times the square of cosine gamma. Let us suppose that the point O is the center of mass of the rigid body. If the principal moments I1, I2 and I3 and the directions of the principal axes with respect to the body are known, that is 3 scalars and 3 angles are given, then the Huygens-Steiner theorem can be applied to calculate the moment of inertia of the body with respect to any axis. In the 3 tables of the moments of inertia shown before for different solids of uniform density, all the moments of inertia are the principal moments of inertia of the solids with respect to their center of mass. For example, the rectangular cuboid with the width a, the length b and the height c has the principal momenta given by 1 over 12 times the mass m of the cuboid times the sum of b squared and c squared, 1 over 12 times the mass m times the sum of c squared and a squared, and 1 over 12 times the mass m of the cuboid times the sum of a squared and b squared. If the width a is equal to the length b but they are not equal to the height c, then the first 2 principal momenta are equal to each other and different from the third one. Thus the ellipsoid of inertia is an ellipsoid of revolution about the principal axis parallel with the edge c of the cuboid. If the width a, the length b and the height c are equal to each other, then all the 3 principal moments of inertia of the cube are the same, and the ellipsoid of inertia of the solid is a sphere. We already saw that the kinetic energy of a rigid body rotating about the z-axis is given by the half of its moment of inertia with respect to the z-axis times the square of the angular velocity of the rotation. In the general case, the kinetic energy of a rigid body rotating about an axis given by the angles alpha, beta and gamma with the angular velocity omega is equal to 1 over 2 times the moment of inertia I sub alpha beta gamma, times omega squared. In the principal axis system of the body, the moment of inertia I sub alpha beta gamma reduced to I1 times the square of cosine alpha, plus I2 times the square of cosine beta, plus I3 times the square of cosine gamma. Then we can write the kinetic energy as 1 over 2 times the sum of I1 times omega squared times the square of cosine alpha, I2 times omega squared times the square of cosine beta, and I3 times omega squared times the square of cosine gamma. We already introduced the angular velocity vector omega, which is parallel with the axis of rotation and its length is equal to the angular velocity. As the figure shows, the components of this vector in the principal axis system are given by omega times cosine alpha, omega times cosine beta, and omega times cosine gamma. If we substitute these expressions into the kinetic energy of the rotating rigid body, then it can be written as 1 over 2 times the sum of the first principal moment of inertia I1 of the body times the square of the first component of its angular velocity omega, its second principal moment of inertia I2 times the square of the second component of the angular velocity omega, and its third principal moment of inertia I3 times the square of the third component of the angular velocity omega. This is the simple form of the rotational energy of the body expressed in its principal axis system with respect to a given point O. We can also express the kinetic energy of a rotating body in terms of its angular momentum L, if we decompose the latter in the principal axis system of the body, where the components of the angular momentum are equal to the product of the corresponding principal moments of inertia and components of the angular velocity vector. By expressing the components of the angular velocity from these equations and inserting the result into the equation obtained above, we can write the kinetic energy as 1 over 2 times the sum of the square of the first component of the angular momentum L over the first principal moment of inertia I1, the square of the second component of the angular momentum L over the second principal moment of inertia I2, and the square of the third component of the angular momentum L over the third principal moment of inertia I3. This form of the kinetic energy of a rotating body is also expressed in the principal axis system with respect to a given point O. As an illustration, we use the example of the rectangular cuboid again. If we substitute the principal moments of inertia for the cuboid into the equation of the kinetic energy, then we can write the latter as 1 over 24 times the mass m of the cuboid, times the sum of three terms. The sum of b squared and c squared times omega 1 squared, the sum of c squared and a squared times omega 2 squared, and the sum of a squared and b squared times omega 3 squared. If the width a, the length b and the height c are equal to each other, then the kinetic energy reduces to the expression stating that 1 over 12 times m times a squared, times the sum of omega 1 squared, omega 2 squared and omega 3 squared. Because the terms in the parentheses just give the square of the angular velocity omega, we obtain 1 over 12 times m times a squared times omega squared, which is the kinetic energy of a cube rotating about an axis passing through of its center.